Now let us see the next topic, that is approximations using derivatives. So that means here we are going to use derivatives to find out the approximate values of certain expressions. Now to recollect the geometrical perspective of looking at derivatives, we know that the derivative represents slope of the tangent to any curve at a particular given point. So here in the figure, the slope of the tangent, that is the green colored line, is nothing but the derivative of that particular function at point A. So we know the definition of f dash of a, which is limit of f of a plus h minus f of a whole upon h as h tends to 0. Now what happens is when h tends to 0, that is h is becoming closer and closer and closer, we can see that the difference between the distances BD and CD, that will also go on reducing. So that means the segments BD and CD will become more and more equal to each other in length, isn't it? So this is where we use the approximation, that is we say that if h is sufficiently small, then we can consider the slope of secant to be equal to slope of tangent only in approximation. So therefore, since f dash of a represents slope of tangent, we will say that f dash of a is approximately equal to this quantity, which is nothing but slope of secant. So therefore we have f of a plus h minus f of a whole divided by h. Now therefore on cross multiplying and transposing the terms, we get the final expression as f of a plus h is approximately equal to f of a plus h into f dash of a. So this is the expression for approximating the value of a function using derivatives. So what it means is, suppose we want to find the value of some function for a particular expression, say a plus h. Now we won't be given that what is a and what is h, we will be given a single value, and we have to identify what we should take as a and what we should take as h. Now the answer to this question depends on the right hand side, that is if you observe in the right hand side, we have to calculate f of a as well as f dash of a. So therefore we must choose a in such a way that it is very convenient to calculate f of a as well as f dash of a. So based on that we decide what is a and h, and typically h will be a very small value, right, as compared to a, because you know the approximation will be better when h is smaller. So therefore we have to choose a and h looking value given, right. Now let us see some of the examples so that this process will be clear. Find the approximate value of square root of 102 using derivatives. Now here first step is to identify the function, that is which function we are dealing with here. So it is nothing but the square root function. So let's consider f of x as root x in general. Now let me write here the expression for approximation which we had derived earlier. We know that f of a plus h is approximately equal to f of a plus h times f dash of a, right. So you see that we are going to need the function as well as its derivative in evaluation. So therefore let us keep ready the derivative expression for root x, which is nothing but we know 1 upon 2 root x, right. Now let's start writing whatever that we want to actually find out. So we have to find out square root of 102, which is nothing but, we can say that it is f of 102, isn't it, because that is a function. Now that is further equal to, here we have to now decide how we should write 102 as something plus something. Now to write a here and h here, what we have seen is a should be selected such that f of a and f dash of a should be easy to calculate. So if you think about that, f of a is nothing but square root of a, isn't it? So which is that number which is closer to 102 and whose square root is very easy to find out? So naturally the answer is a should be selected as 100 because its square root is straight away 10, and therefore h turns out to be simply 2, isn't it? So therefore what we have to find essentially is f of 100 plus 2. Now as per the approximation formula, this is equal to f of 100 plus 2 into f dash of 100, right? So therefore that is approximately equal to, now f of 100 is nothing but square root of 100 as per the definition of function, plus 2 into f dash of 100 is 1 upon 2 root 100. So cancelling 2, we go ahead, root 100 is 10 plus, now in the next term 1 upon root 100 is 1 upon 10, which is 0.1. So therefore we get the final approximate answer as 10.1. So that's the approximate value of 102. Now it's not needed that we should always have the square root to approximate, we can have any other function. So as given here, we have to find the approximate value of tan inverse of 0.999. So that means here we are talking about f of x as nothing but tan inverse of x. So therefore let's keep the derivative ready, which is, we know that it is 1 upon x square plus 1. Now tan inverse of 0.999, this we have to split as tan inverse of sum a plus h. Now what is that value a whose tan inverse we can easily find? So that is clearly the value 1, which is very close to 0.999. So therefore we can write 0.999 as 1 minus 0.001. So therefore h is very small as compared to the value a, and we have to note that h is negative here, alright, but that does not make any difference in the formula. So as per the formula, this is equal to tan inverse of 1, isn't it? That is f of a. Now we have plus h, but since h is negative, I will write that as 0.001 into, here we have derivative of the function of 1. So that is nothing but 1 upon 1 square plus 1, because here we have root of 1 upon x square plus 1. So moving further, we have tan inverse of 1, we know that that is equal to pi by 4, right, minus 0.001 whole divided by 2. Now this value will come approximately equal to 0.785 radians. So after we substitute pi with 3.142 and then simplify, we will get the final answer as 0.785 radians. So that is how we use derivatives to find out the approximate values of some expressions.